Welcome, Professor.
Morning.
Welcome, Professor. Good morning. We're very happy to have you with us, and we're very happy to that you accepted our invitation.
Absolutely.
Okay. So without further ado, I'm gonna hand it over to my dear professor. I'm the head teacher for the course, and I'm gonna hand it over to my professor to welcome you on his side, and then we can have your wonderful time.
Before
Uh,
getting started, I wonder if
sure.
it makes sense. I want to make sure I can figure out the slide sharing. Uh,
Sure. On the top, you can see, I think there are force icon from the right. You
okay,
can share the screen with it.
beautiful. Let me try to figure out that. I apologize. I haven't used this platform before.
Yes. It's new, and I try to give some visuals, and I don't know if they help.
Yeah, help me log on. Sweet. I was just looking for the screen share button. Great. Cool. Beautiful. Great.
Okay, cool. So I'm gonna hand it over to my professor, and then we can have your talk. And thank you.
Hi, Benjamin. Can you hear me?
Perfect.
Nice to have you and nice to meet you. It's our pleasure to have you today. My name is Mohammad Rohban. I am the lecturer of this RL course, and we have regular invited speakers from different topics that we teach every week. So it's nice to have you today, and we are looking forward to hear uh, about your talk. So please feel free to start.
Thank you so much for the kind introduction. I'm super excited to be here, and I'm really looking forward to all the questions the next hour, and then all the during the Q&A in the following 30 minutes.
Thank you so much.
So I'm Benjamin Eysenbach. I'm an assistant professor of computer science here at Princeton University, and I'm super excited to share with you some of the work that me and my students have been working on over the last couple of years. The title of today's talk is Self-Supervised Agents, Learning and Exploring with Minimal Feedback. And when I talk about self-supervision, I'm really going to be thinking about how we can learn from data, from experience, without needing rewards, without needing demonstrations, without needing optimal actions. The huge challenge in generative AI today is how do we generate good data? How do we generate good feedback? And today's talk is going to give some specific algorithmic tools that we might use for lifting some of these limitations. I think reinforcement learning is well positioned to give us ways of automatically generating data. And we're going to see today how we can view reinforcement learning in a way that we can generate that data without expert feedback. And so let's dive in. I want to start with a thought experiment. And this is intended to be interactive. So I hope there's a way that people can react either thumbs up or thumbs down on the platform here. So show of hands, how many people think that a generative image model today, in 2025, May, can generate images different from those seen in its training data set? Is there a way people can raise their hand of some sort? Sweet, okay,
Yes. They can raise their hand, and if they raise their hand, I'm gonna give them the microphone access so they can ask questions.
cool. Okay, so a couple hands there. Um, okay, what about language models? Can language models generate sentences different from those seen in their training data? And now just raise your hand for a vote of yes, not to ask a question, just like, yes, I think they can do this. Okay, 4 out of 14. What is the right analogy for reinforcement learning? This is a rhetorical question, but I like thinking about this question because it's helped thinking about reinforcement learning in the context of the generalization capabilities of other models really has helped expand my mind to what might be possible. A priori, I think generalization and reinforcement learning is typically thought of as sort of a dark art, something like, yeah, maybe it would be nice to have. But In the same way that we've seen wild generalization capabilities for image models, they're able to generate images that are really, really different than those seen in their training data set. And that we've seen similar capabilities for language models. They can generate sentences that are just massively different from those seen in their training data sets. It gives me confidence that the same might be true for reinforcement learning, that it might be possible to build some reinforcement learning agents that can solve tasks that are fundamentally different from those they were trained on, if they're trained on enough tasks. In today's talk, I'm going to argue that one of the key ingredients to find this sort of generalization is to frame reinforcement learning in a self-supervised way that'll allow us to learn on more tasks, on more data. And in today's talk, we'll start to introduce some of the algorithms that allow us to do that, to learn reinforcement, to do reinforcement learning in a self-supervised way. So here's where we're going to go today. I'm going to start by introducing self-supervised reinforcement learning, providing a formal definition, but also giving an example algorithm. And this will lay a foundation for thinking about how is it even possible to think about reinforcement learning if you don't have reward functions. I'll then talk a little bit about some really recent ongoing work in my lab that's started to observe how these self-supervised agents can really unlock new capabilities. And I'll talk a little bit about some generalization properties, and we'll talk about a new benchmark. And part of the reason I wanted to introduce this new benchmark is that it provides a really good jumping off point for folks that want to get involved in the research. So let's get started. This is a deep reinforcement learning course, so I think that the next couple of slides will probably be very obvious to many of you. So I'll go through them rather quickly, but please raise your hand or post in the chat here if you have any questions. So in the typical reinforcement learning problem, we have an environment, we have a policy. The policy outputs actions A in response to observations S. Throughout today's talk, I'm going to assume that the environment, that we're in a fully observed setting, and so the dynamics are Markov, and so the policy is also Markov. In the standard reinforcement learning problem, we also observe rewards S. And without loss of generality, we can assume the rewards only depend on the state. We'll see this makes our lives easier in a couple slides. So the reinforcement learning problem is really exciting because it's so general. It can be used to model games, to model chemical reactions, to model nuclear fusion, to model education. Yet part of that generality, or what comes with that generality, is that it's also a very, very challenging problem. And I think that the challenge of reinforcement learning largely stems from the rewards. And there are a couple different ways of seeing this. One way of seeing it is that unlike in supervised learning, where you get a label for every input, in reinforcement learning, you only get a label, you only get feedback after you take several actions. So in this task here, we have this robot hand, and it might be that you want to get the robot hand to go and pick up this green block and move it over, and then put it down, and then position it in the blue bin. But you might only get the feedback after you've taken 5, 10 actions. And this makes it really hard to figure out, well, which of those actions was the correct action to take. Confounding this is the fact that the observations we're dealing with are often very high dimensional. And so this ratio of number of bits of feedback to number of bits of input is a very, very bad ratio, and it makes the learning really challenging. Now, part of the reason why we have such limited feedback in the reinforcement learning problem is because practically specifying these rewards is really hard. So in this manipulation task that I've been showing here, where we have this robot hand, why should this observation here get a reward of +5? That seems sort of arbitrary. Well, in practice, the reason this state gets a reward of +5 is because a couple of graduate students spent a couple weeks writing this block of code that computes the reward for this observation. However, actually writing this block of code is really, really frustrating. There are all these hyperparameters in here. You might notice this 50 and this 0.01, all these if-else cases. It's really non-trivial to design these rewards, even for experts. And this means that for applications where someone might want to apply reinforcement learning, if you're not an expert, it's basically impossible to apply existing reinforcement learning methods. This becomes even more challenging when you want to look at real-world problems. This reward function here depends on the positions of all the objects. But if you're doing reinforcement learning directly from, say, images, you don't know the positions of all the objects. So you would first have to install some sensors or do some computer vision to figure out the positions of all the objects, even before you could compute your reward function. And so defining these rewards is a really, really challenging problem. And it's challenging not just in robotics. One application we've been playing around with is chemistry. And there, how do we define whether this is a good molecule or a bad molecule? We might want to produce a molecule, say, that's non-toxic, that's safe for humans. But how do you write that in code? How do you say, okay, this molecule is toxic, this molecule is non-toxic? It seems very non-trivial to define that in code. And so in today's talk, we're going to be thinking about how we can start to get the benefits of reinforcement learning without having this massive challenge of reward engineering, without having to write that big block of code. Can we still design reinforcement learning algorithms that can help us out? So that's where we're going to go today. And as a bit of motivation, I want to start by thinking about, in other areas of machine learning, how have we figured out ways of learning without feedback? So in other areas of machine learning, there are these self-supervised techniques that can just look at raw data with no labels and automatically extract useful patterns from those data. So there are a lot of these techniques in computer vision. Some of these techniques are these sort of masked autoencoders or diffusion models. Methods just take an image and cover up pixels of that image or patches of that image, and they try to predict what are the missing pixels or what are the missing patches. And these are the techniques that underlie the big diffusion models that I imagine many of you have used before. And there's similar self-supervised learning techniques in natural language processing. There are methods that look at a sentence and then cover up random words of that sentence, and then you try to predict what are those missing words. Or you cover up the next word of a sentence and you try to predict what are the next words. And in doing so, these methods that predict the missing words give us the foundation for the modern language models that we have today. And so, in fact, one way of seeing modern generative tools, both in vision and in language, is that they rely really heavily on doing self-supervised learning, on doing learning just on raw data, on just big stacks of images or big stacks of sentences without any labels about whether those are good images or bad images. And so seeing the massive success of self-supervised learning in these other domains, in vision and language, it's inspired us to think about how can we develop a foundation for self-supervised reinforcement learning? How can we define reinforcement learning algorithms that similarly don't require any feedback, don't require any rewards? So just to make sure we're all on the same page, I want to introduce a definition of what I mean by self-supervised reinforcement learning. At first pass, self-supervised reinforcement learning might simply mean that we take the reinforcement learning problem and we delete the reward function. We now have formally a controlled Markov process. Maybe more formally, I might say that self-supervised reinforcement learning is the problem of learning policies or models or representations, something that enables us to quickly solve downstream tasks. But we want to learn this policy or model or representation with no rewards and with no demonstrations. So to make this more concrete, I'll talk about one particular type of self-supervised reinforcement learning problem, which is this problem of goal reaching or goal-conditioned reinforcement learning. The input here, it could be an environment without a reward function, or it could just be a data set of, say, videos labeled with actions. These actions are not necessarily the optimal actions. They're not necessarily demonstrations, and we don't have rewards. And the goal, at the end of the day, we want to produce a goal-conditioned policy. That's what we have on the right-hand side. A policy that takes as input the current state of the world and some goal state. And the goal is just an observation that shows what we would like the world to look like. So maybe the state is an image and the goal is another image showing us what we want the world to look like. And the policy should take actions so that eventually we get to this desired goal state. Okay, I'm going to pause here. Are there any questions about the problem statement at this point?
So one quick question: how the goal is specified? Is it specified through a particular state, or do we have other means of doing it?
This is a super good question. So in the next couple slides, I'm going to assume that the goal is given by a state observation. And so for this robot manipulation task here, the goal could just look like this image over here. At the end of today's talk, I'll talk a little bit about different ways of specifying goals. One example is via language.
I see. And so the learning should happen in a way that the algorithm is prepared to go to every possible goal. Is that true?
We would very much like that. What we'll see today is an algorithm. Yes, yeah, that is where we're headed.
All right. Thank you.
It's a really good question. Are there any other questions? Great, let's move on. So I want to now introduce an algorithm that we found pretty effective for solving some of these goal-reaching tasks. It's an algorithm we designed about 3 years ago, but it's continued to surprise us by giving us new methods for new tasks and new interest, and it keeps the phenomenon we observe have also continued to surprise us. And this will just give one example of a goal condition algorithm, one way of learning this goal condition policy without needing rewards. And there's several other algorithms that we could talk about later if folks are interested. So this algorithm works by using a form of contrastive learning. Contrastive learning is a way of taking data and learning representations from those data. And we do this using a form of temporal contrastive learning. This is a tool that's been around for a long time, especially in other domains, but we've found a way of applying it to the reinforcement learning setting that allows us to get optimal policies. And so what we're going to do is we're going to learn two encoders. One encoder is an encoder of state action pairs that maps pairs of states and actions to a representation. And the other is a goal encoder that takes just a future state observation and maps it to a representation. And we're going to learn these encoders using two terms. One term says that when we take our time series data, when we take our video, we should look at a state and an action and sample some future state. And we want to optimize the encoders to give similar representations to states that occur nearby in time on the same video. And then if we look at states from different videos, we should optimize these encoders so that observations from different videos have dissimilar representations. So the intuition here is that the similarity between the representations should tell us similarity in time. How likely is it that you could get from one state action pair to some other state over some time horizon? Now, one detail that will turn out to be important is that when we're sampling these positive examples, these future states, we're going to sample them from a certain geometric distribution. And so they're most likely going to be 1 or 2 or 3 steps in the future, but they could be 4 or 5 or more steps in the future. And this geometric distribution will allow us to prove some important theoretical properties about this method. Now, one important detail here is that one of these encoders, the state action encoder, depends on the action. And what that means is that after we've learned these representations, we'll be able to directly use the representations for figuring out what is the best action to take if we want to get from one state to some future state. Remember, at the end of the day, it's these actions that we want to figure out. Now, for folks that have seen contrastive learning before, we can draw a certain analogy. So typically when contrastive learning is introduced, say in a computer vision course, we think about applying it to images. You take an image and then an augmented version of that same image, and then you optimize your representations to be similar for images of the same person and dissimilar for images of different people. Now, the main challenge in applying contrastive learning is defining what these augmentations are. Are you going to rotate the image? Are you going to change the colors, the saturation? What we're doing is we're doing augmentation using dynamics, using time. So what we're doing is we're saying when we look at a video, if we take a frame of that video, we construct the augmented frame of that video by jumping forward in time. And that doesn't require any engineering. It simply requires data. Another way of seeing what these representations are doing is viewing them as a sort of embedding, a way of embedding time series data so that states that occur nearby in time are given similar representations, and states that occur more distantly in time are given more distant representations. So the intuition here is that once we've learned these representations, we should be able to use them for figuring out what are the states I'm likely to visit when I want to go from one state to another state, and what are the best actions to take if I want to get from point A to point B. So let's see how that works. As an example, let's go back to this manipulation task that we started today's talk with. We have this robot arm here. This robot arm can move up, down, left, right, forward, backwards, and it has a grip where it can open and close. And let's say that we want to navigate from this current state to this goal state shown here, where the key difference is that the robot arm has gone down and picked up the block and moved it into the blue bin. And as a thought experiment, let's imagine we just had two actions, A1 and A2. So we can think about these representations as points lying on a sphere. We'll assume for now the representations are normalized, so they lie on a sphere. It could be a very high dimensional sphere. And because the state action representation depends on the action, for each of these actions, A1 and A2, we get different representations. And so if we just look at this picture here, we can compare the similarity between one state action representation and the goal representation, and another state action representation and the goal representation. And so just based on this figure here, I want to see a show of hands for who thinks we should take action A1. And show of hands for who thinks we should take action A2. And who is confused? Great. Okay. So yeah, after we've learned these representations, we can exactly look at their similarity to figure out what is the best action to take. And so here, it seems like A2 is the best action. So we would take action A2, and then we will get to some new state. And then based on this new state, we would do a similar computation, figuring out what is the best action to take here. And that's exactly how the method works. We define the policy as selecting whichever action A has a state action representation with a most similar dot product to the goal representation. So let's just wrap this up. Let's see how the complete algorithm works. We start with data, a data set that's of not demonstration. It could just be of random data, of random state action pairs with no rewards. We then do this temporal contrastive learning to learn these representations, a state action representation and a goal representation. And then we use these representations to extract a goal reaching policy, a goal condition policy that selects the actions given the state and the goal. Now at this point, we can be done. You can take this policy and go solve your task. Or you could take this policy and go back and collect some more data. And depending on the problem setting you're in, sometimes collecting more data can further improve performance. Now, I think at this point it's worth stepping back and providing a little bit of history. So we started this talk by saying designing rewards is really hard. It's really frustrating for the graduate students to have to sit down and write those big blocks of red code. And so ordinarily, reinforcement learning requires defining and learning from a lot of rewards. And on the surface, it seems like these goal conditioned reinforcement learning problems should require lots of rewards, because now you're not solving one task, but many tasks. And this is typically how prior work has viewed these goal conditioned RL problems. These goal conditioned RL problems have been around for almost 60, 70 years. In fact, some of the earliest work in AI in the 1950s and 60s was working on goal conditioned reinforcement learning. But typically, it's been viewed as a really, really challenging problem because you're solving not one problem, but many problems. But what we've seen here in this talk is that there's a way of defining these goal conditioned reinforcement learning problems in a way such that they don't require any rewards at all. And from an engineering perspective, this is really appealing because it means that you no longer have to define these rewards, that big giant red block of code, when you want to go solve some new problem. And aesthetically, we'll see how it draws some really nice connections to other areas of generative AI. And we'll see that in a couple slides. So practically, this method, it ends up even outperforming methods that do use rewards. So here I'm showing a visualization of what our approach does on this manipulation task when we tell the policy to try to get to this goal state up here. And a very good prior method completely fails to solve this task. We've shown this method outperforms a number of prior methods, but now I want to jump forward and highlight two really interesting applications that we've seen of these self-supervised reinforcement learning methods. One is in robotic control. This is a collaboration done with Changyi Chung and Homer Walk. And so the problem that we were looking at was tabletop rearrangement. We have a robot shown up here. Is this Widow X robot? It's a pretty low-cost robot. It's a couple $1,000s. And that makes it really fairly accessible. It's a couple orders of magnitude cheaper than most robot arms today. But it also means that it's really hard to control because the plastic parts wear down, the motors are kind of shaky. And we wanted to get the robot to rearrange the table so it looks like this goal on the right-hand side. And there are two key differences between the image on the left and the image on the right. The first one is that the robot hand has moved to the upper left-hand side of the image. And the second is that this red spoon has moved to the left side of the image. And from a robotics perspective, there are a lot of things that make this problem really challenging. First is that we're going to try to learn a policy that can do this manipulation problem from suboptimal data. We don't have any demonstrations, so we're going to be learning from a bunch of noisy data of the robot just doing random things. A second thing is that we don't know the positions of all the objects. We're doing this directly from pixels, from images. And third, we're going to do this in the setting where we can't learn by trial and error, but instead we just have a fixed bucket of data. And from that fixed bucket of data, we're trying to pull out this goal-reaching policy. So there are a lot of things that make this problem really challenging. And so it's not surprising that the best prior method we could find, it fails to solve this task. And one thing you might notice is that this prior method, it fails in a sort of interesting way. It successfully moves the robot arm to this position on the left side of the screen, but it just ignores the spoon. And maybe that sort of makes sense. The spoon is only a small fraction of the image. Now, in contrast, when we evaluated our method, we found that the robot arm successfully went out of its way to pick up this red spoon and move it to the left side of the table and place it there, and then finally reposition the robot arm in roughly the right position. And one thing I want to emphasize here is that it was able to learn how to do this without needing anyone to define those complex reward functions. The graduate students, Changyi and Homer, working on this project, they never had to sit down and write that big, giant, ugly block of red code. And because of that, they could use the same policy with no more training, with no more data, with no more gradient updates to solve new tasks, just by prompting it with a new goal. So here we gave the robot a different goal, where now this can has been moved to the top of the table. And with no more training, we can just evaluate the policy. And we see that it roughly succeeds at solving this task as well. I think it's sort of interesting now to pop back up and think about the motivation at the start of this talk, when we were thinking about the generalization capabilities of language models and the generalization capabilities of vision models. The way we test the generalization capabilities there is by prompting those models on with things that were not seen in the training data. And so note that we can do the same thing here. We can prompt this model with all sorts of images that it hasn't seen during training and see how well it does. And like those models, this reinforcement learning model is trained primarily on unlabeled data. In fact, it's trained entirely on unlabeled data. And so I think that these self-supervised methods are a really promising hint or promising approach for thinking about how we can develop reinforcement learning methods that exhibit the same sort of strong generalization capabilities that generative models in other domains do. And I want to briefly talk about one other interesting application. This one we didn't take part in, but it is a really cool application of these contrastive reinforcement learning methods. This was done by some folks at a healthcare company nearby. They were looking at controlling ultrasound devices. There's this certain type of ultrasound device that you put down someone's throat, and then you can use this ultrasound to take ultrasound pictures of someone's heart. And this is a really challenging control problem. You have to this camera down here has all these knobs that you can control to focus the camera and to turn the camera around. And so the operators and the doctors controlling these cameras have a really hard time focusing and getting the correct images. So what this team did was they used these contrastive reinforcement learning methods to treat this as a goal-reaching problem. The goal here was a desired picture of someone's heart from a certain angle and a certain viewpoint. And after training, they gave the system this desired picture, and then the system could automatically figure out how do you change these control parameters so to get the ultrasound to take the desired picture. And I think this just emphasizes how these goal-reaching problems are potentially really widely applicable, and how, because they don't need rewards, it makes it a lot easier for people in new domains to adopt these tools. So popping back up one level, we started this talk by emphasizing the key challenge in reinforcement learning. Typically, when we talk about reinforcement learning, at least when I teach reinforcement learning in my course here at Princeton, we assume that we're given the rewards. We assume, okay, someone gives you a game and you can read the score on the top right-hand corner. But a lot of practical problems don't have rewards readily accessible, and defining the rewards is a big challenge. And today we saw how by treating the reinforcement learning problem as a goal-reaching problem, we can avoid defining rewards. One of the key tricks that we saw for doing this was to think about self-supervised learning. We thought about self-supervised learning and vision and language, and how that was a really useful tool for giving rise to the powerful generative AI methods that we have today. And this method that I introduced, this temporal contrastive learning method, gave us an example of how we can use self-supervised learning for reinforcement learning. Now, in the next couple of slides, I want to argue that reinforcement learning is not actually that different from generative AI. In fact, when we think about self-supervised reinforcement learning, there's a sense in which it is a generative model. And I want to walk you through what I mean here, because I think it helps really reframe what reinforcement learning methods are capable of. So let's think about what a generative model is. A generative model, typically, is trained on examples of images, say images of cats. And then to sample from that generative model, you perform some iterative procedure, typically going through some sequence of layers or iteratively denoising an image to produce a new sample. Now, reinforcement learning methods can be seen as doing something very, very similar. In particular, these goal-reaching methods were trained on a big data set. And then to sample an outcome, we also performed iterative computation, where the policy would take an action, and then the environment would give us some new observation, the policy would take another action, the environment would give us new observation. We would go around this loop many, many times iteratively, and then after doing this maybe 100 times, we get some output. And so what reinforcement learning is just a different way of defining a way of sampling from a certain generative model. While our image generative models consist entirely of known parameters, this reinforcement learning generative model consists of a combination of some policy parameters that we've trained and an environment that we don't even know. But at the end of the day, it gives us a way of sampling outcomes. Another way of seeing this is that when a lot of generative image models today, you can prompt them. You give them a text description, such as a castle in the mountains, and they perform this iterative computation, iteratively denoising an image to eventually come to some desired outcome. How might we build reinforcement learning methods that do something similar, where we give them a prompt, say an image or a text description of build a castle surrounded by mountains, and then the robot performs hundreds or thousands or millions of actions to actually build that castle by interacting with the world. So again, we want to learn this mapping from an input prompt, maybe an image, maybe language, to an output state. But now we're thinking about mapping the inputs to the outputs by actually interacting with the environment. So I think that we can think about reinforcement learning agents as a generative model. And that's what I mean when I say that self-supervised reinforcement learning, it really is a sort of generative AI. And so I think moving forward, we might see that generative AI methods start to look a whole lot more like reinforcement learning methods rather than the sort of vision and language methods that we've seen before. And in the remaining of the talk, I want to highlight a couple ongoing research efforts where we've started to push in this direction, where we've started to see what really is possible with these self-supervised methods. So I want to start with the elephant in the room. I've been primarily focusing on goal-reaching problems, but not every problem is a goal-reaching problem. How do you tackle problems beyond goal-reaching with self-supervised reinforcement learning? Well, to do that, we need to introduce a little bit of theory, trying to think about what mathematically are these representations learning. Before I said intuitively, they tell us the likelihood of getting from one state to some other state, but can we formalize that in math? Our key theoretical result here is a relationship between these representations and Q values. In particular, you can prove that the dot product between these representations, the similarity between these representations, exactly corresponds to a discounted sum of rewards. And this reward function here is a very natural one. It's the likelihood that your next state is equal to the goal. But conveniently, when we introduced this algorithm, we never actually computed this reward function. And so I'm introducing this reward function purely for analysis reasons. You never actually have to compute this. And what this theory tells us for one is that when we're comparing the similarity between these representations, that's not just a heuristic, but rather that's a principled thing to do. Comparing these representations exactly corresponds to selecting actions that maximize your Q value. And that's the same thing that you saw, that you probably have seen already in this course for algorithms like DQN. And we'll see in a little bit how this same analysis gives us a way of solving problems beyond goal-reaching tasks. One small subtle note here is that up in this right-hand corner here, I have this beta. And what that means is that the algorithm I've introduced so far is estimating the Q value for the behavioral policy, the future expected rewards if you acted the same way that you did when you were collecting the data. Now, sometimes you might want to do a sort of Q-learning or SARSA style method, where you instead estimate the Q value that you would get if you were acting according to a different policy. And it turns out there's a way of adapting this contrastive learning procedure to do off-policy evaluation. And I'm going to skip over the details now, but the key idea is that you can do bootstrapping using these contrastive features by comparing the similarities at one time step to the similarities at the next time step. And it ends up closely resembling an idea known as the successor representation that's popular in neuroscience. So the key reason I bring up this theory is that by showing that these representations encode probabilities, it gives us a way of solving problems beyond just goal-reaching problems. So for goal-reaching problems, we could use these representations to estimate the likelihood of getting to the desired goal state, and then for figuring out what is the best action to maximize that probability. Now, there's some problems where there are multiple outcomes that are all good. Maybe you want to clean your bedroom, but there are several different configurations of your bedroom that could be called clean. You might not care about the order of the books on your bookshelf or the order of the pillows on your couch. And so there, to solve problems where there are multiple good outcomes, you could simply provide the system with multiple examples of good outcomes. And now, by using these representations, you can estimate the likelihood of getting to any of these good outcomes, and then taking actions that maximize the likelihood of getting to any of these good outcomes. Similarly, you can extend this to the setting where, to the fully general setting, where you have a small number of states labeled with rewards. Maybe you know one state that has a reward of 8, one state that has a reward of 3, one state that has a reward of -10, another with a reward of -5. And given just these 4 states and the representations, you can estimate the likelihood of getting to the state with reward +8, and the likelihood of getting to the state with reward +3, and so on, and then select actions to maximize your future rewards, where your future rewards are just the likelihood of getting to each of these states times the reward at each of these 4 states. And we've shown that these extensions work very effectively. So the key takeaway here is that these representations are useful not just for solving goal-reaching problems, but also for solving more general reinforcement learning problems. Before going on to talking about some of the most recent research, I want to pause to see if there are any questions at this point.
I have a quick question. Can you hear
Yes.
my voice?
Perfect.
Yeah. So in contrastive learning, we know that if we apply the augmentation in the regular uh, case of self-supervised learning, like um, SimCLR and techniques like that, if we apply augmentations that totally change the image, there is no hope to learn a meaningful representation. And we have to keep a balance between how much we change the image and whether or not the task that we are asking the encoder to solve being something trivial. So if you apply too small augmentation, that also doesn't work. So here it sounds like you pick an action that reaches some goal state in the future, and you treat those two state actions and goal state as positive pairs. How do you make sure that the same problem doesn't happen here? Do you enforce a threshold on the time horizon that you expect that action to result in the goal state, or do you have other mechanisms to make sure that problem doesn't happen?
In practice, we haven't found this to be a huge problem. The most important parameter we have is this parameter that tells us how far into the future are we going to look. So when we sample the future state here, we're sampling it according to a geometric distribution with probability with parameter 1 minus gamma. And so if we select a very small value of gamma, like gamma equals 0.5, then the future states are mostly going to be 1 or 2 steps in the future. And so it's a very easy classification problem. If you select a very large value of gamma, like gamma equals 0.999, then the future states are, on average, going to be 1,000 time steps in the future. And that's going to be a very, very challenging problem. We found that the algorithm is pretty robust to this choice of gamma. In practice, we ended up using a value of 0.99, but that's mostly to be consistent with prior work in the literature, not because it works much better or worse than other values. There is a kind of there is one setting where this issue definitely does show up, and that's in settings where every trajectory, when it's really easy to distinguish one trajectory from another trajectory. For example, let's imagine that I take a couple pictures out my window, and or let's say that I take a video outside my window here, and then I take another video in next month, another video the month after that. The trees outside my window, they're going to look different every month. And so even though I want these features to pick up temporal information within a single video, the representations would probably just pick up how each video looks different from the previous video, because one video doesn't have leaves on the trees and the next video does have leaves on the trees. And so there's a variant of this method where instead of sampling the negative examples from different videos, we sample them from the same video, but just much further away in time. And that increases the difficulty of the classification problem, but can result in learning better features. So I hope that answers the question. Largely, it's not an issue, but when it is an issue, there are ways of combating it by thinking about how do you sample the negative examples.
May I ask a question too?
Absolutely.
Uh, I have many questions, but I ask just some of them. My first question is, are really temporally far states far semantically? Because, for example, the mountain car example, the classic one, when a
Yeah.
car goes up and then goes down, it can be in very similar state, for example, to its initial state. How do you contrast these two? They are not really semantically away from each other.
This is a really, really good point. Um, the um, and so when I say that we're learning representations so that the distance between the representations corresponds to the distance in time, I'm saying this in an average sense. And so you're absolutely right that there can be examples where states that were far apart in time, uh, actually are often occur nearby in time as well. But part of the reason why I wanted to introduce this theory is it actually gives us some theoretical grounding for confidently saying, yes, these representations are telling us the correct thing. They are telling us the likelihood of getting from one state to some other state at some point in time. One way of seeing this is that um, in that example you mentioned, where you have the mountain car, and let's say that you're looking at one state and a nearby state, and that nearby state, uh, you could have gotten to it if you first went up the mountain and then down the mountain. Well, the likelihood of sampling that transition is going to be much lower than the likelihood of sampling the transition where you just go from this position to this position. Because this shorter path, because the likelihood of sampling a start goal pair is depends on gamma to the number of time steps that have elapsed. And so you're much, much more likely to sample this state goal pair along this first path when you went from the state to the goal than along this longer path when you first went from the state up the mountain and then down again. In fact, it's exponentially more likely to sample a shorter path. And that's part of the reason why this doesn't end up being a problem.
Okay, I got it. Thank you. And I have two other questions. Another one is, how do you deal with continuous action space? And because you use argmax there, and for continuous action space, the only thing that I have in mind right now is to take gradient with respect to action, gradient of difference between current state and the goal state. Is it the only possible way, or is any other way around?
Yeah. So in practice, what we do is have you seen algorithms like DDPG or TD3?
Yes, yes.
Cool. So we do exactly the same thing that those algorithms do. So we learn a policy that where the objective for the policy is to sample actions that maximize this inner product.
Mhm. I see.
And so in practice, this algorithm is actually very easy to implement on top of an implementation of SAC or TD3 or DDPG. You simply modify your actor loss to, instead of using the Q value, use this inner product, and you modify your critic loss to, instead of using the regular TD loss, to use this contrastive loss.
I see. I see. Thank you. And for the last question, how do you deal with partially observable environments? Because in those states, you cannot contrast observation with each other. They should be the full history or embedding of history, and it is embedding on embedding. It gets harder, I believe.
That is an open problem. We haven't solved it yet.
Oh, okay. Thank you.
I think the easiest way of doing it would be to do exactly like you suggested, to think about sequences of states and then use some sort of sequence model like an LSTM or a transformer, but we haven't tried that yet.
I see. Thank you. Thank you.
Any other questions before we move on? Yeah, go ahead.
Do you have my voice?
Perfect.
I have a question about the goal condition RL. In goal condition, for example, in a vision task, which we compute the dot product between the goal state and the current state, does this limit our exploration in the environment? Because in each state that I am, I want to close as possible to the goal state. And maybe there are some states that are not really similar to the goal state, at least in our feature space. And those can lead us to the better states. I think this exploration may be a bit limitation for goal condition, or I'm wrong.
To the contrary, we find that the exploration is much stronger than alternative methods. And in a couple slides, I'll talk a little bit about this. I think part of the reason why is that when we think about these goal-reaching tasks, we're only saying what we want the agent to do, not how we want it to do it. And because we aren't telling the agent how it should do it, it has to automatically try to figure out what is the best way of solving the task. And so, for example, when you look at mazes, we end up seeing pretty effective exploration, exploring lots of different parts of the maze before it eventually finds the shortest path.
I see. Thank you.
Great. In these last few minutes, I want to talk about some of the most recent research that we've been doing using these contrastive methods. Cool. So our goal that, like we started the talk with, was thinking about how do we build reinforcement learning methods that are like generative models that could be prompted to do nearly everything. And I want to highlight some recent work that's taken some steps towards this. So if we think about what have been the successes or what has helped cause these other areas of generative AI to be so successful, I think perhaps the most important component is self-supervised feedback. We've already seen today how we can build reinforcement learning methods with self-supervised feedback. But I think there are a couple other important ingredients. One is the capacity to train on lots and lots of data. Two is the ability to use lots of compute. And three is having standardized benchmarks so we can compare different methods on a level playing field. So to get these next three benefits, together with some collaborators, we designed a new benchmark that allows us to compare methods on a level playing field and to use lots more compute and data to see how leveraging more compute and data can improve performance. And so this is a new benchmark that we've been calling JAX GCRL. JAX is the programming language and goal condition reinforcement learning. There's a link to the repo down here. And I want to highlight some of the key properties of this benchmark that has made it really fun to use. The most important property is that it's really fast. When I was doing my PhD, it used to take several hours to a couple days to run experiments that now just take a couple minutes on one GPU. And so I think this has just made the research process a lot more fun because now you can iterate on algorithms in a couple minutes. It makes the problem of algorithm design feel a lot more like data science. It also makes it a lot easier to run experiments for millions or billions of time steps. And previously, only those experiments could only be done in industry with people that had lots and lots of GPUs. I want to highlight some of the tasks here. Some of them are pretty easy, some of them are really hard and are still open problems. So one of the tasks is this embodied Sokoban problem, where this quadruped is trying to run to a goal that's hidden back here, and first has to push this block out of the way to get there. Here we can see it. This next episode, I'm going to hide the goal over here. This next task is a football task where the ant has to dribble the soccer ball towards this location here. And you see it's fairly good at football. And so this gives you a sense of the sorts of problems that these contrastive algorithms can solve. We also have a new benchmark that looks at the offline setting. So if you want to see, okay, if you just are given a fixed data set, what are the sorts of policies you can learn? This benchmark is a really great way of doing that. Both these benchmarks have really good documentation. And so if you're looking to get involved in the research, I'd highly recommend looking at these two benchmarks. The next thing I want to talk a little bit about is generalization. And so when we think about generalization in machine learning broadly, often we're thinking about generalization across perceptual differences. Say we want a neural network to produce similar outputs for an image and an augmented version of that same image. In this project, we were thinking about a kind of wacky notion of generalization that's unique to the reinforcement learning problem. This notion of generalization that we were calling horizon generalization. And the idea is that when we have a goal condition policy, if we give it a state action pair, a state goal pair, and it produces some action, if instead of telling it to get to a goal, we tell it to get to a waypoint on the route to that goal, so instead of trying to get really far away, just try to get to a first intermediate waypoint, you should take a similar action. And so this is a notion of invariance. You want your policy to produce similar actions for different inputs, or for transformed inputs. And what Kathy and Vivek proved is that if you have this invariance property, then your policy will generalize with respect to the horizon. And what I mean here is that you can now, if your policy satisfies this property, you can train it on just easy tasks, say task reaching goals within the smaller circle, and then the policy provably will generalize to be able to reach goals that are more further away. And so I think this notion of generalization is really powerful for thinking about how do we build reinforcement learning agents that really can generalize new things that are radically different than those they were trained on. We also have found that data augmentation can be pretty useful for achieving this sort of generalization. So self-supervised reinforcement learning, it really can be seen as a form of generative AI. And if we want to figure out how do we build agents that can do anything, there are a couple of sort of hints that we've seen over the last couple of months that this really should be possible. And I want to briefly highlight some of those hints. The first is that these representations seem to have really intriguing properties. And so before, when we were looking at the similarity between these representations, we actually can think about what these intermediate points, what these intermediate representations look like. So if we start with a prior method, an alternative method, a variational autoencoder, if you visualize these intermediate waypoints, you end up seeing that the representations have captured the contents of the scene, but not anything about time. In contrast, with these temporal contrastive learning methods, these intermediate representations not only capture the contents of your image, but also how to solve the task. They also capture the physics. And so when you interpolate in representation space between this observation here and this observation here, you end up generating a plan. And this was entirely unexpected. We didn't expect this to happen. But I think that this gives us some hints that these representations really are capturing useful bits of information. Since then, we've done some theory to actually prove why this interpolation should happen. The second interesting property that we've seen gets back to the question that was asked earlier about exploration. So typically, when we train these goal condition methods, we train them on goals of varying difficulties. And so when we collect the data, when we say, sometimes we say, okay, try to get to a very difficult goal. Sometimes we say, try to get to an easier goal. Often we only actually care about the performance on one difficult goal. But our intuition, based on prior work, is that if you only collected data, if you only ever tried to get to a very, very distant goal, it would be very hard to do the exploration. But to our surprise, when we're using these temporal contrastive learning methods, doing data collection by always commanding one difficult goal actually works. In fact, it often works better than collecting data using these goals of varying difficulties. And this actually pretty profoundly changed how I think about the exploration problem. Previously, I used to think that exploration happened by first finding a route to the goal and then finding faster and faster routes to the goal. But what this project showed is that even before these agents have ever found a path to the goal, the agent here is trying to move the green block to the blue bin. The agent here is trying to put the lid on the box. Even before these agents have ever successfully solved the task, they're starting to do interesting exploration. They're starting to knock the blocks around, push the objects around. And so I think what this shows is that there's something about these contrastive reinforcement learning methods that allows them to do really effective exploration, even before they've ever solved the task for the first time. So he's only here around 19,000 trials when they first solved the task. And we see that that similar things happen in the multi-agent setting, that there's a similar emergence of exploration here. And the last hint that we found pretty intriguing is that these methods benefit significantly from scale. So most reinforcement learning methods use architectures that are about 4 layers deep. And prior work has found that making networks deeper don't seem to increase performance. But with these self-supervised methods, we find that increasing the depth of networks can significantly improve performance. And I think the key reason why gets back to the start of this talk, that we're doing self-supervised learning. And because we're doing the self-supervised learning, what this means is that we're getting many bits of supervision for free. We're just extracting bits from these raw unlabeled data. And because we're getting all of these extra bits for free, I think this helps explain why we're able to train models that are much bigger. And this in turn results in learning behaviors that more effectively solve a number of tasks. So I'm going to end there. I think that the key challenge in reinforcement learning today is rewards. I think self-supervised learning is a really powerful tool for figuring out how do we get the benefits of reinforcement learning without the challenges of designing rewards. And I think more broadly, it gives us a roadmap for thinking about how do we build reinforcement learning agents that truly will be able to do anything, including things that are far beyond what they were trained to do. I'll end here, and I'm happy to take any questions for the remaining 30 minutes. Thank you. Oh, one last note, if you want to get involved in the research, here is a link to the repository for the code base that I talked about in the middle of the talk.
Thank you so much, Benjamin. I have a quick question. In training LLMs, RL has recently been found to be a success story, like the DeepSeek story and other things. So do you believe that these methods that you introduced in this talk, could they be useful in that context as well? What's your take on that?
Absolutely. In fact, we're currently working on it. The methods like the DeepSeek R1 method are really powerful for certain types of problems, for problems where it's easy to define the rewards. You might notice that most of the successes of reinforcement learning for language models are in settings where the rewards are easy to define, where you have these nice verifiable rewards. Now, this explains why the language models are really effective at things like coding, where you can write test cases to check the correctness of code, and math, where we already have proof checkers that can check whether your proof is correct. But in settings like dialogue, it's a lot harder to define a reward function for saying, did the chatbot convince the patient to take their medication every day? And my hope is that there are all these potential applications of language modeling that will be unlocked by thinking about these problems as goal-reaching problems.
I see. Thank you so much.
I also have a question. My question is why doing greedy action is good here, but not good in RL itself. You know, what you're doing here is taking greedy action that makes you closer to the representation of goal state that you want to go. I claim that there could be a path that is closer, but not in embedding space. I don't know how to phrase it correctly, but I just want to know why greedy action is good here.
I agree this is super counterintuitive. If we think about solving a maze, greedy action selection is not a good idea. Another example, my office is on the 2nd floor. So if I want to get down to the road down there, I could try to jump out my window. That is that would correspond to greedy action selection. But that very obviously is not the best way of getting outside the building. I should take the stairs, not jump out the window. Part of the reason why the theory here is important is that it helps explain why greedy action selection is useful. I assume you've probably seen the policy improvement theorem in your course. And what that says is that choosing actions that maximize the Q value, that's the right thing to do. If you repeat that, you'll eventually get the optimal policy. And so showing that greedy action selection corresponds to selecting actions that maximize the Q value, this helps give us some reassurance that greedy action selection is actually a good idea.
I see. I see. Now it makes sense. Thank you. Thank you.
Hi, do you have my voice?
Perfect.
And thank you for awesome presentation. I have a question about negative samples and how we choose them. Actually, this
Yeah.
question comes to my mind from studies about debiasing contrastive learning in computer vision I've seen. So my question is, to what extent could that be important here? Are there any positive correlations that we punish in our contrastive loss?
Can you elaborate a bit?
Okay, yeah. Actually, I wonder when we punish our negative samples within our batch, could we have some positive correlations between the positive trajectory and the negative trajectory? For example, we could have some certain robot movement in our trajectory, but toward different goals. So, should we classify them as negative samples to each other or not?
I'm not entirely sure I understand the question. I think one thing that definitely is true is that sometimes the samples that you use as negatives, maybe let's go back to um, um, the negative samples here. Sometimes the negative examples are actually positive examples. Sometimes we
Yeah.
get it wrong, but that's actually okay because what's important for classification is the frequency with which something occurs as a positive example versus a negative example. And the representations are basically encoding the relative frequency of positive examples versus negative examples. Formally, this problem is sometimes known as positive unlabeled classification.
Thank you. Thank you so much.
If folks also have questions about just like the research in general or reinforcement learning or graduate school or anything else, feel free to ask those questions as well. Why you should do a PhD in reinforcement learning?
I have another question since nobody asked question. I have a lot of them. I can ask
Great.
so more questions. My question is, how do you define reward in that theorem that you showed us that it is equivalent to maximizing the return, not the reward itself? What is the reward there? How do you define the reward that is equal to achieving the goal?
So how is the reward here defined?
Yes, exactly.
So this is purely for analysis. What you can prove is that the inner product here is equivalent to the discounted sum of rewards, where the reward is the likelihood of getting to a state at the next time step. In tabular settings, this is just a 1 if you're at the goal and a 0 if you're not at the goal. So I think the tabular setting is a bit easier to think about.
Okay, I see. See. Thank you.
Another question from my side, Benjamin. So you mentioned why um, taking a PhD with a thesis defined on RL, and that is the question for many of my graduate students here at Sharif.
Yeah.
They're saying that so this mostly applies to the master students actually, uh, where it takes like 2 years for the research to be completed. So some of them ask why we should work on RL problems because, it's quite unlikely to gain some significant achievements in such a short period of time. So what is your take on that? Do you believe could we do quick researches on reinforcement learning in 2 years or so, or it should be subject of PhD studies?
I definitely think we can. Um, and as a couple examples of this, I guess talk about like the timeline for several of these things. Um, so this project that Grace and Michael worked on, Grace was a master's student, Michael was an undergrad, and they completed this project in about 6 months. And so uh, that's very doable. This project that Kirayu and Shlok worked on, Kirayu and Shlok are both undergraduate students, and they completed this project in less than 6 months on top of their coursework. And similarly, this project that Kevin and Ishan worked on, honestly, was probably October, February, like 4 or 5 months. And so it's very, very possible to do amazing research in a short amount of time.
Cool. That's awesome. So, are these projects? Did these projects require some significant computational resources as well, or it was just like conventional amount of resources?
This The project that Kevin and Ishan worked on did require a fair number of GPUs. These big networks just train really slowly, and so for running the experiments, we needed a lot of GPUs. For the multi-agent ones, I don't think we needed that many GPUs. I think
Mhm.
that um, rough, I think roughly speaking, if you have less than one GPU per student, it's hard to do the research. Um, but I think that you'd be able to get by with one GPU per person.
I see. I see. Thank you so much. So, Arash, is there any question left?
I don't think so. I don't see any question from the audience. So I think we can finish the talk here if there's no other question. Okay. Okay. So thank you, Professor, for accepting our invite, and we had a wonderful time having you giving us the talk.
Thank you again for the invite. I really enjoyed all the questions.
Thank you, and have a good rest of the day.
Thank you so much. Have a nice day.